Welcome back. Today we begin our series on sleep and memory. You all may have heard about the impact of a good night's sleep on the next day performance, on either an examination or a performance that you have practiced on the piano. What we will attempt to do in the next series of lectures is to dig deep and to uncover the structural and molecular changes that occur in the brain that underlie the phenomenon that a good night's sleep prepares you for improved performance the next day. It gets even more dramatic, and that is without sleep. If you are sleep deprived, you will eventually die, and you will die of brain failure, which will precipitate organ failure down the road. And we need to understand why this is. Why is it necessary for brains to sleep? And what do brains do while we are asleep? Now, you all are familiar with the concept of REM versus non-REM sleep, rapid eye movement sleep and deep sleep. And you know that you dream during rapid eye movement sleep. And we will attempt to elucidate what dreaming actually does in the economy of the brain. But today we will deal with two papers that appeared in the same issue of Science magazine just a week or so ago that address in somewhat different ways a similar theme, and that is, what does the brain do during slow wave or deep sleep that have to do with the restoration of the brain, the rebalancing of synapses, and the preservation of memory. Now here in the first slide, you see kind of the classical canonical theory of the relationship of sleep and memory. So there are a number of different waves involved here. You can see there is the thamalo-cortical tract here that yields a certain wave pattern. We have spindle ripple effects that are related to processing in the hippocampus. It's been shown, and I will anticipate this now from a future lecture, that when a rodent like a mouse or a rat learns to find a way through a maze and goes to sleep, it will rehearse, or its hippocampus will rehearse the route to find it more efficiently the next day by running these spindle ripple events through the hippocampus. Now, the idea then is that the hippocampus is a temporary storage device, and somehow during sleep there is a transfer into long-term storage into the neocortex, and we can see the hallmark of this brain activity in the various oscillatory potentials that the brain yields during the sleep time. Now here is the first paper that we will discuss in some detail. Here is really the anchor paper, and named Giulio Tononi. He is a sleep researcher at the University of Wisconsin. Now, this is not the only claim to fame that he has. He is also the originator of an innovative and increasingly popular theory of consciousness, an unresolved deep riddle in philosophy and neuroscience is, how does the brain create consciousness, or how does the brain become conscious? There are deep philosophical issues embedded here, which we will address in a separate lecture. But he's the one who invented a theory called integrated information theory, which in one fell swoop eliminates a lot of the philosophical confusion surrounding the idea of how is it that atoms and empty space, the void and atoms, in some kind of combination, are able to create the phenomenon of consciousness without invoking any magical and supernatural powers or any new ontology. So this is Giulio Tononi here. So his day job is to investigate sleep. And so he was attempting to prove a point that he has made earlier, also in an edition of Neuron, namely to prove the existence of a theory called the synaptic homeostatic hypothesis. So we will get to this in just a second. And here is a first statement of this paper, namely, the cortex, the human cortex, contains about 16 billion neurons. Now that's a lot less than the about 100 billion in the total brain. Interestingly, the vast majority of neurons is found in the cerebellum. You don't need a cerebellum to generate consciousness. There are rare cases of agenesis of the cerebellum, which result in some clumsiness and difficulty with motor sequences, but do not impair in the least the phenomenon of consciousness. So all these billions of neurons in the cerebellum do not contribute to consciousness. However, the 16 billion neurons, of course, in the cortex are critical for consciousness. Now, in the mouse, we have about 14 million neurons, and each neuron can harbor thousands of synapses. Now, of the billions of cortical synapses of the adult mouse, 80% are excitatory. And the majority of these are on what's called dendritic spines. Now, this poses a problem, because if the excitatory neurons are exciting themselves over and over again, you might run into a ceiling effect or saturation effect, where things just can't be any more excited than they already are. So these authors then propose to test an idea that perhaps during sleep there is a general reset of the total excitability of these synapses. Everything gets reduced or normalized to a mean level, at the same time though sparing those special synaptic connections that have to do with newly acquired learning in the wakefulness preceding sleep. Now, a couple of items we need to mention here to make the paper understandable, namely that spine size, these spines that are involved in the synapses, are tightly correlated with synaptic strength. And synaptic strength, of course, being a measure of learning. When you learn something, neurons fire together and the synaptic strength connection is increased, which is thought to be a hallmark of newly acquired learning. The volume of the spine head, I will show you a photo in a minute here, is strongly correlated with other structures that are similar, and with the number of vesicles located in the presynapse. Also, the number of presynaptic AMPA receptors and the amplitude of AMPA-mediated synaptic currents is also correlated with these spine sizes. So just a reminder here, if we had unconstrained long-term potentiation, which is another word for the accumulated excitatory activity of certain neurons, we wind up with a saturation effect, such as here. The idea of synaptic scaling proposes that we need to bring down the excitability after a period of wakefulness to a more manageable level, so that during the next period of wakefulness you can embark on your daily activities and engage in new learning as you practice your piano or you practice your calculus problems at home. So here then is the synaptic homeostatic hypothesis as proposed by Giulio Tononi and others. Changes in synaptic strength are the primary mechanism mediating learning and memory. Synaptic potentiation and depression must be balanced to avoid either saturation or obliteration of neuronal signaling and memory traces. So this hypothesis then argues that owing to the energy and signaling requirements, learning should occur primarily through synaptic potentiation during wake times, leading to a net increase in synaptic strength. The overall synaptic renormalization by net weakening should occur during sleep, because during sleep your brain is disconnected from the environment. It is literally offline. So no new information can get in, either sensory or otherwise, giving the brain a chance to review its current synaptic status in an unbiased way and reset the synaptic excitability in such a way that excessive activation is tuned down, but at the same time preserving those critical new connections that have been strengthened because of learning that has taken place just prior to the sleep period. So there are some intriguing implications that this hypothesis makes. Namely, billions of cortical excitatory synapses should increase in size, literally in size, after a wakeful period and decrease after sleep, independent of circadian time. So it should be a strictly learning-mediated effect. Furthermore, although synaptic renormalization should affect a majority of synapses, it should also be selective and allow for both stability and plasticity. And here are some references that I encourage you to look up. Now, in this paper, we focus on what's called the ASI, which is the average synaptic the surface area of direct contact between axonal bouton and spine, as a structural measure of synaptic strength, because the authors have previously shown that the size literally corresponds with the previous state of activation of these neurons. So here then is what they did, and it's a truly heroic endeavor. So they looked at a mouse brain here and collected synapses, either at spontaneous wakefulness and forced wakefulness, keeping the poor mouse awake although it wanted to sleep, and during sleep time. And then go ahead and count all these little boutons here that are attached to these spines. Not only that, but also measure the volume and the specific contact that they have made. So here, for example, you have the spine head, and here is the ASI region, namely that part that contacts the spine. Here is your good old dendrite, and here is the main axon. Up here we have an outline of the experiment, just showing that you have spontaneous wakefulness and forced wakefulness and sleep, and you can see the different sleep parameters listed here. Here is just an enhanced presentation of this. This is an electron micrograph that shows you in a color-coded way the structures that correspond to the structures in here. And this is the finding. Now you see there is tremendous clustering and overlap going on. However, the main message is that during sleep, here, the axon-spine interface, ASI, is significantly decreased in size. Now this doesn't happen in a few neurons, it happens in tens of thousands of neurons. Now imagine what this means. You go to sleep and you think your brain is resting and recovering. really what's going on is a massive reconstruction of your brain. While you sleep and rest, crews are at work. And I'm going to show you some of the crew workers later in a subsequent paper. And their job is to prune these synapses, not by elimination, but by reducing the size through a number of biochemical mechanisms that we will come to shortly. But there is a wholesale shrinkage going on in an effort to equalize the excitability of the total synapse population in such a way that when you wake up, you are ready to go. And after your cup of coffee, your neurons are set up in such a way that they have ample reservoir and ample ability to get excited again and not carry over all the action potential residues that have accumulated during the previous period of wakefulness. Here, of course, you see the structures that have been analyzed in detail, and you can see that wakefulness and enforced wakefulness are associated with an increase in these structures. So that was the key finding. There are other findings in this paper, but in terms of using our time effectively, this is the key message. Now, this was a very heroic paper to go in and literally identify these structures and measure their size. These are extremely small, and it takes a great deal of technical expertise and effort to pull this off. So here then is kind of what they are looking for. You have spine dynamics. You see the awake spine here, and a certain number of receptors are here present. And then in the sleep phase, you see there is a reorganization in such a way that excitatory receptor numbers are largely decreased. So where are these things located? Well, you have the axon here, a synapse, you have the cell body and all the dendrites, of course, and this is the structure that they are looking at. The dendrites connecting to other structures and forming synapses. The theory then is this. In the phase of wakefulness, when learning takes place, you have an increase overall in synaptic strength. And during sleep, you have an overall decrease in synaptic strength connection. And the reason is that if you didn't do this, you would have a saturation of plasticity. You literally would run out of excitatory synapses that you can subject to long-term potentiation, and learning stops in its track. It's as though the brain is overheating and cannot take in any more information. During sleep, though, a global reset occurs. All synapses, more or less, are subject to a reorganization which leads to a desaturation of plasticity and allowing for a new day to occur during which the brain is refreshed and ready to go. Now, the implications for learning, of course, are clear. If you are sleep deprived and you don't get a good night's sleep before an examination, maybe several nights in a row, those days that you attempt to learn new material that were not preceded by adequate reset and adequate sleep will be totally wasted, because you just can't learn anymore because your system is saturated. There's no more learning capacity left in your neurons unless you use the sleep reset button in an adequate way. So here's another way of putting this. Here you have this young lady during a wakeful period, and she is meeting a new young attractive man all kinds of amazing things happened. We learn who he is, where he has come from. A lot of synaptic potentiation takes place globally in the cortex. This is accompanied by increased firing rate of the locus coeruleus, which is kind of the engine to keep alertness going. It uses noradrenaline, which will make a replay later when I show you the next paper. And so this is the encoding phase where we learn everything we can learn about this new event that occurred in our life. Now, during sleep, we are offline. We are disconnected from our environment. No sensory input comes in. And this allows the brain, in the absence of any interference by you or anybody else, to survey what has happened during the day. An unbiased review of all the potentiation, all the long-term potentiation that has occurred across synapses in the cortex, and cool down the entire excitatory potential, but do it in such a way that new information is preserved and protected. So low levels of neuromodulation combined with this synchronous off and on firing of many neurons during non-REM sleep, such as slow wave, spindles, and sharp waves, mediate these events. We will, in subsequent lectures, dissect in great detail the physiological relevance of these different waves. A paper has just appeared in the Proceedings of the National Academy of Sciences, which proposes to have found a critical link between the two papers I'm discussing for you today and the physiology of the different EEG events that are observed in REM and non-REM sleep. Now, by contrast, synapses belonging to circuits that were only rarely activated during the wakefulness hours are progressively depressed and eventually eliminated over many sleep-wake cycles. So it's the internal bookkeeping of the brain that occurs in this model of sleep. What are some of the supporting lines of evidence? Well, for example, glutamate AMPA receptors increase during waking hours, as shown here. AMPA receptors are the business end of excitatory synapses. They drive the sodium influx and depolarization. You can also see that in wakefulness, cortical evoked potentials, particularly the slope of the cortical evoked potential changes, which is an indirect measure of excitability of the neurons. So these data were available and in part were the trigger to formulate this particular hypothesis of this reset of the brain during sleeping hours. Now, there are human experiments as well, again focusing on the slope of evoked potential, and you can see that during sleep deprivation, the size of the evoked potential slope is increasing, and during sleep it is coming back to normal. So all this fits together with this homeostatic hypothesis. There are also ultrastructural findings, which, as you have seen in the beginning of this talk, and which this key paper elucidated in great detail, as has been observed that during sleep there is a loss of dendritic spines. In an enriched environment during wakefulness, there is an enrichment in dendritic spines as well, and this can be quantitated, and it is a significant event. This, in fact, prompted the investigation of Tononi and others in the paper that I presented at the beginning of this talk. Now, Let's just recapitulate and do a short historical aside, namely the idea of long-term potentiation, which really underlies this entire work. This was discovered first, believe it or not, in 1988. A lifetime ago, a couple of generations ago of neuroscience almost, and the key findings were this, that there were two receptors in the synapse, namely an NMDA receptor here, and what was called a QK receptor here, now called AMPA receptor. And it was found that in order to activate the NMDA receptor here, which had a magnesium block, you need to fire these AMPA receptors with some frequency to release the magnesium block to facilitate the entry of calcium. Calcium being the magic juice, the magic molecule that makes all kinds of interesting things happen. If you recall back our talks on memory and the work of Eric Kandel elucidated in great detail how calcium and calcium-modulated protein kinases were very essential in the case of aplysia, the common C slack, in learning some very, very basic behaviors. So this is the underlying work that goes back to 1988. So it took a couple of generations of neuroscientists to really nail this down. Now, this knowledge is being applied to the study of sleep. So the model we had of a receptor used to be that a receptor sits in the membrane and waits for things to happen, a ligand to approach, bind to a receptor, and then an intracellular event would be triggered. This picture has dramatically changed. We now know that receptors can move laterally in the membrane, left and right. Receptors are taken into the membrane, but also internalized again into the cell and put into the lysosome, dissolved, recycled. There is a dynamic exchange of receptor molecules that is going on almost constantly. And this has been shown in many cases for the AMPA receptor in excitatory glutaminergic synapses. Here then is this very scary image of the complexity of an excitatory neuron. Here is our familiar NMDA receptor, of course, and here is our AMPA receptor, and you can see the number of molecules that are involved. I want you to concentrate in particular on PSD95, the postsynaptic density molecule 95, which will make its appearance in the next paper that we are discussing. Now, the receptors are anchored in the membrane and are connected to other important proteins just inside the membrane through the mediation of PD95 and other molecules such as 4,1N and many others. Here are a collection of protein kinases. These are the kinases that get activated by a signal coming in through the receptors, activation of protein kinases, and then all kinds of interesting things happen within the cell. Now, here are a couple of interesting molecules such as Homer1 and Shank1. Shank is very critical in schizophrenia research. There have been genetic polymorphism of the Shank protein family that have been linked to the risk for schizophrenia. Homer1A will play an important role in the next paper, as I will outline to you shortly. Now, we have mentioned two receptors on this neuron, the NMDA and the AMPA receptor. There's also the metabotropic glutamine receptor. that is not really involved in the business of rapid neurotransmission, but rather in the tuning and maintenance of a certain internal milieu of the cell that makes it possible for all these wonderful events to take place. Here are some references that document what we have just talked about. So this is paper number 2. I mentioned to you Homer 1A. Here it is. Homer 1A is one of those early proteins that couple in some way events that happen at the receptor site to things that happen inside the cell. So this paper in the same issue of Science magazine now attempts to elucidate a role for Homer 1A in the homeostatic scaling down of excitatory synapses during sleep. So let's just dig into this and see what happens here. So again, the homeostatic scaling down weakens excitatory synapses, as we have discussed, through removal and dephosphorylation of synaptic AMPA-type glutamate receptors. So this is a somewhat different way of stating the hypothesis. Whereas Tononi and colleagues emphasize the structural changes at the dendritic spines, these authors here focus on the biochemical events that are taking place, such as the dephosphorylation and trafficking of AMPA receptors. So they have done a number of biochemical tricks and have shown that the weakening of synapses through removal and dephosphorylation of AMPA receptors are critically important in these changes. So in summary, their data suggests they feel that homeostatic scaling down, a global form of synaptic plasticity, is active during sleep to remodel synapses and participate in the consolidation of what they call contextual memories. Here is the model that they came up with, and I'll show you some of the data supporting this. So in the waking state, you have our postsynaptic density 95, which we discussed earlier. Here we have the metabotrophic glutamine receptor, and when everything is well, then Homer 1 links this complex to yet another effector protein inside the cell. Now, during sleep, this connection is uncoupled. And this uncoupling will lead to all kinds of restructuring in the cell, such as, for example, a dephosphorylation of AMPA receptors and a tuning down of the readiness of the excitatory synapse to respond to a new excitatory impulse coming down the pike. So what they did then is this. They were able to purify these structures, these proteins. Here you see PSD95, for example, and PSD95 is here again. Here is tubulin. This is a gel which separates proteins according to size. And here is the key result. So what this then shows is that certain AMPA receptor subtypes, in fact subunits composing the AMPA receptors, are decreased during sleep. See, this entire population here is decreased. So that is the key finding. So why is that? What is the mechanism that drives the decrease of the production of these AMPA-type receptors that are attached to PSD95 in the synapse? And what they homed in on is Homer 1A. As you may know, mice are very interesting creatures because we can engineer mice transgenically. Especially, we can knock out specific genes in mice in a very selective way. And here is a mouse that is lacking Homer 1A. It just doesn't have the gene. It cannot produce the Homer 1A protein. And as you can see, nothing much happens here. All the proteins are at the same level because without HOMA1A being present, this particular link in the chain, these events that happen during sleep just are unable to occur. Now, during sleep, in the wild type, HOMA1A is dramatically increased over control levels, indicating then, by the way, here you see HOMA1A on the gel, and here is the wild type. And in the next slide, you can see what happens during wakefulness and sleep. Here is an immunoprecipitation where an antibody was used to pull down the complex of IP3R, one of the coupling proteins of HOMA1A. And during sleep, this complex is largely decreased. However, in the knockout mouse, this is, by the way, SHANK1, during sleep is not affected. And here is the metabotrophic glutamine receptor that is also decreased during sleep. Now let's go back one slide perhaps. Okay, so here we see the different co-precipitations, and here is sleep and sleep, and you can see that HOMA1L is here, and HOMA1L is here again, and during sleep time, the coupling between the HOMA1L and the IP3A is indicated by the co-precipitation that this complex is decreased during sleep. Now, the model then looks like this. We have a coupling normally of the HOMA1L with the IP3A. Pharmacological experiments now done with adenosine. Adenosine is a sleep-promoting compound. Adenosine will lead to increased coupling of the metabotropic receptor through HOMA1A, and you promote sleep in this way. Noradrenaline will decouple this event. And as I told you before, noradrenaline produced by the locus coeruleus. The noradrenaline neurons innervate widely the cortical areas. Noradrenaline, being a wakefulness driver, decouples this event. If we go back a couple of slides to the original model, I want to remind you again that here is the HOMA molecule, which in the mutant mouse is absent and leads to an abrogation of all these effects. And the normal coupling is from metabotrophic receptor to IP3A, and then all the protein kinases, effector molecules in the cell. So this would be the abrogation if you lack the HOMA1A molecule. So let's summarize. These two papers have shown in different ways evidence to support the homeostatic synaptic plasticity model of sleep. It's predicted that if you don't normalize the neuronal excitability of cortical neurons in some way, you will wind up with an excitability catastrophe, that the brain will overload and you will no longer be able to respond to excitatory inputs after a while because the neuronal system is just overloaded and exhausted. So in sleep, the hypothesis is that because the brain is offline, no sensory inputs are coming in, affords the opportunity to review what has happened during the day and invoke this decoupling mechanism involving HOMA1A and a shrinkage of the size of the dendritic spine connections, synaptic spine connections, in concert to de-escalate the excitatory potential of the brain, to normalize it, and get the brain ready for another interesting new day upon awakening and be responsive to excitatory inputs. So that is the theory, and I think the proof is quite strong, emphasizing the importance of sleep for learning. There is a point of diminishing return. All-nighters before an exam are a total waste of time, not because of lack of trying and effort, but because your synaptic reservoir, your synaptic system that is allowing you to learn is already at the end of its capacity and overloaded. If you allow a good period of sleep, you allow the brain to go through this restorative decoupling and resetting of the biochemical machinery that allows your neuron two things. Number one, be ready for the next day, and number two, preserve those connections that have been preferentially activated during the previous learning experience, and make sure that those learned experiences are stored in a more permanent way. So this was our first installment on a lecture series on sleep and memory. There is a whole lot more. This is a very rapidly emerging field, which is interesting for all of us in terms of sleep, wakefulness, budgeting. We all are sleep deprived to some extent, but also as a powerful tool in looking into the mechanisms of the brain in terms of how the brain manages its budget and manages its acquisition and storage of memories. Thank you very much for your attention. We'll see you soon for another presentation from behavioralhealth2000.com.